Moving charges and magnetism. Introduction. Both electricity and magnetism have been known for more than 2000 years. However, it was only about 200 years ago, in 1820, that it was realized that they were intimately related. In the summer of 1820, the Danish physicist Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle, which has the straight wire as its center and has its plane perpendicular to the wire. This situation is depicted in figure. It is noticeable when the current is large and the needle sufficiently close to the wire so that the Earth's magnetic field may be ignored. Reversing the direction of the current reverses the orientation of the needle. The deflection increases on increasing the current or bringing the needle closer to the wire. Iron fillings sprinkled around the wire arrange themselves in concentric circles with the wire as the center. Ørsted concluded that moving charges or currents produced a magnetic field in the surrounding space. Following this, there was intense experimentation. In 1864, the laws obeyed by electricity and magnetism were unified and formulated by James Maxwell, who then realized that light was electromagnetic waves. Radio waves were discovered by Hertz and produced by J.C. Bose and G. Marconi by the end of the 19th century. A remarkable scientific and technological progress has taken place in the 20th century. This is due to our increased understanding of electromagnetism and the invention of devices for production, amplification, transmission, and detection of electromagnetic waves. Magnetic force. 1. Sources and fields. Before we introduce the concept of a magnetic field B, we shall recapitulate what we have learnt in previous chapter about the electric field E. We have seen that the interaction between two charges can be considered in two stages. The charge Q, the source of the field, produces an electric field E where E is equal to Q r cap upon 4 pi epsilon 0 r square. Equation number 1, where r cap is unit vector along r and the field E is a vector field. A charge Q interacts with this field and experiences a force F given by F is equal to Q E is equal to Q r cap upon 4 pi epsilon 0 r square. Equation number 2. As pointed out in the previous chapter, the field E is not just an artifact but has a physical role. It can convey energy and momentum and is not established instantaneously but takes finite time to propagate. The concept of a field was specially stressed by Faraday and was incorporated by Maxwell in his unification of electricity and magnetism. In addition to depending on each point in space, it can also vary with time, that is, be a function of time. In our discussions in this chapter, we will assume that the fields do not change with time. The field at a particular point can be due to one or more charges. If there are more charges, the fields add vectorially. This is called the principle of superposition. Once the field is known, the force on a test charge is given by equation number 2. Just as static charges produce an electric field, the currents or moving charges produce in addition a magnetic field, denoted by Br, again a vector field. It has several basic properties identical to the electric field. It is defined at each point in space and can in addition depend on time. Experimentally, it is found to obey the principle of superposition. The magnetic field of several sources is the vector addition of magnetic field of each individual source. 2. Magnetic field Lorentz force. Let us suppose that there is a point charge Q that is moving with a velocity v and located at r at a given time t. In presence of both the electric field ER and the magnetic field BR, the force on an electric charge Q due to both of them can be written as F is equal to Q ER plus V into BR is equal to F electric plus F magnetic. Equation number 3. This force was given first by H. A. Lorentz based on the extensive experiments of Ampere and others. It is called the Lorentz force. If we look at the interaction with the magnetic field, we find the following features. 1. It depends on Q, V and B, that is charge of the particle, the velocity and the magnetic field. Force on a negative charge is opposite to that on a positive charge. 2. The magnetic force Q, V into B includes a vector product of velocity and magnetic field. The vector product makes the force due to magnetic field vanish, means becomes zero, if velocity and magnetic field are parallel or antiparallel. The force acts in a sideways direction perpendicular to both the velocity and the magnetic field. Its direction is given by the screw rule or right hand rule for vector or cross product as illustrated in figure. 3. The magnetic force is zero if charge is not moving, as then mode of V is equal to 0. Only a moving charge feels the magnetic force. The expressions for the magnetic force helps us to define the unit of the magnetic field. If one takes Q, F and V all to be unity in the force equation, F is equal to Q, V into B is equal to QVB sin theta n cap, where theta is the angle between V and B. The magnitude of magnetic field B is 1 SI unit when the force acting on a unit charge, that is 1 C, moving perpendicular to B with a speed 1 meter per second is 1 Newton. Dimensionally, we have B is equal to F upon QV and the unit of B are Newton second per coulomb meter. This unit is called Tesla, that is T, named after Nikola Tesla. 1856 to 1943. Tesla is a rather large unit. A smaller unit that is non-SI called Gauss is equal to 10 raised to minus 4 Tesla is also often used. The Earth's magnetic field is about 3.6 into 10 raised to minus 5 Tesla. Table lists magnetic fields over a wide range in the universe. Order of magnitudes of magnetic fields in a variety of physical situations. Physical situation. Magnitude of B, that is in Tesla. Surface of a neutron star, 10 raised to 8. Typical large field in a laboratory. 1. Near a small bar magnet, 10 raised to minus 2. On the Earth's surface, 10 raised to minus 5. Human nerve fiber, 10 raised to minus 10. Interstellar space, 10 raised to minus 12. 3. Magnetic force on a current carrying conductor. We can extend the analysis for force due to magnetic field on a single moving charge to a straight rod carrying current. Consider a rod of a uniform cross-sectional area A and length L. We shall assume one kind of mobile carriers as in a conductor, here electrons. Let the number density of these mobile charge carriers in it be n. Then the total number of mobile charge carriers in it is NAL. For a steady current I in this conducting rod, we may assume that each mobile carrier has an average drift velocity Vd. In the presence of an external magnetic field B, the force on these carriers is F is equal to NAL QVD into B, where Q is the value of the charge on a carrier. Now NQVD is the current density J and mode of NQVD is the current I. Thus, F is equal to NQEVD AL into B is equal to J AL into B is equal to IL into B, where L is the vector of magnitude L, the length of the rod, and with a direction identical to the current I. The current I is not a vector. In the last step leading to equation number 4, we have transferred the vector sign from J to L. Equation 4 holds for a straight rod. In this equation, B is the external magnetic field. It is not the field produced by the current carrying rod. If the wire has an arbitrary shape, we can calculate the Lorentz force on it by considering it as a collection of linear strips dlj and summing F is equal to summation from J I dl j into B. This summation can be converted to an integral in most cases. Example 1. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of the magnetic field? Solution. From equation 4, we find that there is an upward force F of magnitude ILB. For mid-air suspension, this must be balanced by the force due to gravity. mg is equal to ILB. B is equal to mg upon I into L is equal to 0.2 into 9.8 divided by 2 into 1.5 is equal to 0.65 Tesla. It would have been sufficient to specify m upon L, the mass per unit length of the wire. The Earth's magnetic field is approximately 4 into 10 raised to 5 Tesla, and we have ignored it. Example 2. If the magnetic field is parallel to the positive y-axis and the charged particle is moving along the positive x-axis, which way would the Lorentz force be? For A, an electron that is negative charge, B, a proton that is positive charge. Solution. The velocity v of particle is along the x-axis, while B, the magnetic field, is along the x-axis. So V into B is along the z-axis, that is screw rule or right hand thumb rule. So A, for electron, it will be along minus z-axis. B, for a positive charge, that is proton, the force is along plus z-axis. 3. Motion in a magnetic field. We will now consider in greater detail the motion of a charge moving in a magnetic field. We have learned in mechanics that a force on a particle does work if the force has a component along or opposed to the direction of motion of the particle. In the case of motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle. So, no work is done and no change in the magnitude of the velocity is produced, though the direction of momentum may be changed. Notice that this is unlike the force due to an electric field, QE, which can have a component parallel or antiparallel to motion and thus can transfer energy in addition to momentum. We shall consider motion of a charged particle in a uniform magnetic field. First, consider the case of V perpendicular to B. The perpendicular force QV into B acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other. If velocity has a component along B, this component remains unchanged, as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is as before a circular one, thereby producing a helical motion. If r is the radius of the circular part of a particle, then a force of mv squared upon r acts perpendicular to the path towards the center of the circle and is called the centripetal force. If the velocity v is perpendicular to the magnetic field B, the magnetic force is perpendicular to both V and B and acts like a centripetal force. It has a magnitude QVB, equating the two expressions for centripetal force. mv squared upon r is equal to QVB, which gives r is equal to mv upon QB for the radius of the circle described by the charged particle. The larger the momentum, the larger is the radius and bigger the circle described. If omega is the angular frequency, then v is equal to omega r. So, omega is equal to 2 pi into v is equal to qv upon m, which is independent of the velocity or energy. Here, v is the frequency of rotation. The independence of v from energy has important application in the design of a cyclotron. The time taken for one revolution is t is equal to 2 pi upon omega is equal to 1 upon v. If there is a component of the velocity parallel to the magnetic field that is denoted by parallel, it will make the particle move along the field and the path of the particle would be a helical one. The distance moved along the magnetic field in one rotation is called pitch, P. Using equation 6a, we have P is equal to V parallel T is equal to 2 pi m V parallel upon QB. Equation number 6b. The radius of the circular component of motion is called the radius of the helix. Example 3. What is the radius of the path of an electron, that is mass 9 into 10 raised to minus 31 kilogram and charge 1.6 into 10 raised to minus 19 coulomb, moving at a speed of 3 into 10 raised to 7 meter per second in a magnetic field of 6 into 10 raised to minus 4 Tesla perpendicular to it. What is its frequency? Calculate its energy in kilo electron volt. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Solution. Using equation 5, we find R is equal to mv upon qb is equal to 9 into 10 raised to minus 31 kilogram into 3 into 10 raised to 7 meter per second divided by 1.6 into 10 raised to minus 19 coulomb into 6 into 10 raised to minus 4 Tesla is equal to 28.12 into 10 raised to minus 2 meter is equal to 28.12 centimeter. V is equal to V upon 2 pi r is equal to 17 into 10 raised to 6 second inverse is equal to 17 into 10 raised to 6 hertz is equal to 17 megahertz. E is equal to 1/2 mv square is equal to 1/2 into 9 into 10 raised to minus 31 kilogram into 9 into 10 raised to 14 meter square per second square is equal to 40.5 into 10 raised to minus 17 joule is approximately equal to 4 into 10 raised to minus 16 joule is equal to 2.5 kilo electron volt. 4. Motion in combined electric and magnetic fields. Velocity sector. A charge q moving with velocity v in presence of both electric and magnetic fields experiences a force given by equation number 3, that is F is equal to QE plus V into B is equal to FE plus FB. We shall consider the simple case in which electric and magnetic fields are perpendicular to each other and also perpendicular to the velocity of the particle. We have E is equal to EJ cap, B is equal to BK cap, V is equal to VI cap, FE is equal to QE is equal to QE J cap, FB is equal to QV into B is equal to QVI cap minus bk cap is equal to minus qvb j cap. Therefore, F is equal to QE minus VB j cap. Thus, electric and magnetic forces are in opposite directions as shown in the figure. Suppose we adjust the value of E and B such that magnitude of the two forces are equal. Then, total force on the charge is 0 and the charge will move in the fields undeflected. This happens when QE is equal to QVB or V is equal to E upon B. Equation number 7. This condition can be used to select charged particles of a particular velocity out of a beam containing charges moving with different speeds, means irrespective of their charge and mass. The crossed E and B fields therefore serve as a velocity selector. Only particles with speed E upon B pass undeflected through the region of crossed fields. This method was employed by J.J. Thomson in 1897 to measure the charge to mass ratio, that is E upon m, of an electron. The principle is also employed in mass spectrometer, a device that separates charged particles, usually ions, according to their charge to mass ratio. Cyclotron. The cyclotron is a machine to accelerate charged particles or ions to high energies. It was invented by E.O. Lawrence and M.S. Livingston in 1934 to investigate nuclear structure. The cyclotron uses both electric and magnetic fields in combination to increase the energy of charged particles. As the fields are perpendicular to each other, they are called crossed fields. Cyclotron uses the fact that the frequency of revolution of the charged particle in a magnetic field is independent of its energy. The particles move most of the time inside two semicircular disc-like metal containers, D1 and D2, which are called Ds as they look like the letter D. Figure shows a schematic view of the cyclotron. Inside the metal boxes, the particle is shielded and is not acted on by the electric field. The magnetic field, however, acts on the particle and makes it go round in a circular path inside a D. Every time the particle moves from one D to another, it is acted upon by the electric field. The sign of the electric field is changed alternately, in tune with the circular motion of the particle. This ensures that the particle is always accelerated by the electric field. Each time the acceleration increases the energy of the particle. As energy increases, the radius of the circular path increases. So, the path is a spiral one. The whole assembly is evacuated to minimize collisions between the ions and the air molecules. A high-frequency alternating voltage is applied to the disc. In the sketch shown in figure, positive ions or positively charged particles, for example protons, are released at the center P. They move in a semicircular path in one of the discs and arrive in the gap between the discs in a time interval T upon 2, where T, the period of revolution, is given by equation 6. T is equal to 1 upon Vc is equal to 2 pi m upon Qb, or Vc is equal to Qb upon 2 pi m. Equation number 8. This frequency is called the cyclotron frequency for obvious reasons and is denoted by Vc. The frequency Va of the applied voltage is adjusted so that the polarity of the disc is reversed in the same time. That is, takes the ions to complete one half of the revolution. The requirement Va is equal to Vc is called the resonance condition. The phase of the supply is adjusted so that when the positive ions arrive at the edge of D1, D2 is at a lower potential, and the ions are accelerated across the gap. Inside the disk, the particles travel in a region free of the electric field. The increase in their kinetic energy is QV each time they cross from one D to another, where V refers to the voltage across the disk at that time. From equation 5, it is clear that the radius of their path goes on increasing each time their kinetic energy increases. The ions are repeatedly accelerated across the disk until they have the required energy to have a radius approximately that of the disk. They are then deflected by a magnetic field and leave the system via an exit slit. From equation 5, we have V is equal to QBR upon M. Equation number 9, where R is the radius of the trajectory at exit and equals the radius of a D. Hence, the kinetic energy of the ions is 1/2 mv square is equal to Q square B square R square upon 2m. Equation number 10. The operation of the cyclotron is based on the fact that the time for one revolution of an ion is independent of its speed or radius of its orbit. The cyclotron is used to bombard nuclei with energetic particles so accelerated by it and study the resulting nuclear reactions. It is also used to implant ions into solids and modify their properties or even synthesize new materials. It is used in hospitals to produce radioactive substances which can be used in diagnosis and treatment. Example 4. A cyclotron's oscillator frequency is 10 MHz. What should be the operating magnetic field for accelerating protons? If the radius of its disk is 60 cm, what is the kinetic energy? That is mega electron volt of the proton beam produced by the accelerator. That is E is equal to 1.60 into 10 raised to minus 19 coulomb. MP is equal to 1.67 into 10 raised to minus 27 kilogram. 1 MeV is equal to 1.6 into 10 raised to minus 13 joule. Solution. The oscillator frequency should be the same as proton's cyclotron frequency. Using equation 5 and 6a, we have B is equal to 2 pi mv upon q is equal to 6.3 into 1.67 into 10 raised to minus 27 into 10 raised to 7 divided by 1.6 into 10 raised to minus 19 is equal to 0.66 Tesla. Final velocity of protons is V is equal to R into 2 pi V is equal to 0.6 m into 2 into 3.14 into 10 into 10 raised to 6 is equal to 3.78 into 10 raised to 7 meter per second. E is equal to 1/2 mv square is equal to 1.67 into 10 raised to minus 27 into 14.3 into 10 raised to 14 divided by 2 into 1.6 into 10 raised to minus 13 is equal to 7 mega electron volt. 5. Magnetic field due to a current element. Biot-Savart law. All magnetic fields are due to currents or moving charges and due to intrinsic magnetic moments of particles. The relation between current and the magnetic field it produces. It is given by the Biot-Savart law. Figure shows a finite conductor XY carrying current I. Consider an infinitesimal element dl of the conductor. The magnetic field dB due to this element is to be determined at a point P, which is at a distance r from it. Let theta be the angle between dl and the displacement vector r. According to Biot-Savart law, the magnitude of the magnetic field dB is proportional to the current I. the element length mode of dl and inversely proportional to the square of the distance r. Its direction is perpendicular to the plane containing dl and r. Thus, in vector notation, dB is directly proportional to idl into r upon r cube is equal to mu 0 upon 4 pi into idl into r upon r cube. Equation number 11a, where mu 0 upon 4 pi is the constant of proportionality. The above expression holds when the medium is vacuum. The magnitude of this field is mod of dB is equal to mu 0 upon 4 pi into idl into sine theta upon r square. Equation number 11b, where we have used the property of cross product. Equation 11a constitutes our basic equation for the magnetic field. The proportionality constant in SI units has the exact value. Mu 0 upon 4 pi is equal to 10 raised to minus 7 Tesla into meter per ampere. Equation number 11c. We call mu 0 the permeability of free space or vacuum. The Biot-Savart law for the magnetic field has certain similarities as well as differences with the Coulomb's law for the electrostatic field. Some of these are: 1. Both are long range, since both depend inversely on the square of distance from the source to the point of interest. The principle of superposition applies to both fields. In this connection, note that the magnetic field is linear in the source IDL, just as the electrostatic field is linear in its source, the electric charge. 2. The electrostatic field is produced by a scalar source, namely the electric charge. The magnetic field is produced by a vector source IDL. 3. The electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector r and the current element IDL. 4. There is an angle dependence in the Biot-Savart law, which is not present in the electrostatic case. In figure, the magnetic field at any point in the direction of dl, that is the dashed line, is 0. Along this line, theta is equal to 0, sine theta is equal to 0, and from equation 11a, mod of dB is equal to 0. There is an interesting relation between epsilon 0, the permittivity of free space, mu 0, the permeability of free space, and c, the speed of light in vacuum. Epsilon 0 mu 0 is equal to 4 pi epsilon 0 into mu 0 upon 4 pi is equal to 1 divided by 9 into 10 raised to 9 into 10 raised to minus 7 is equal to 1 divided by 3 into 10 raised to 8 whole square is equal to 1 upon c square. Since the speed of light in vacuum is constant, the product mu 0 epsilon 0 is fixed in magnitude. Choosing the value of either epsilon 0 or mu 0 fixes the value of the other. In SI units, mu 0 is fixed to be equal to 4 pi into 10 raised to minus 7 in magnitude. Example 5. An element delta L is equal to delta X into I cap is placed at the origin and carries a large current I is equal to 10 ampere. What is the magnetic field on the y-axis at a distance of 0.5 meter? Delta X is equal to 1 centimeter. Solution. Mod of dB is equal to mu 0 upon 4 pi into IDL sine theta upon r square using equation 11. dl is equal to delta X is equal to 10 raised to minus 2 m. I is equal to 10 a. R is equal to 0.5 m is equal to y. Mu 0 upon 4 pi is equal to 10 raised to minus 7 tm upon a. Theta is equal to 90 degree. Sin theta is equal to 1. Mod of dB is equal to 10 raised to minus 7 into 10 into 10 raised to minus 2 into 1 divided by 25 into 10 raised to minus 2 is equal to 4 into 10 raised to minus 8t. The direction of the field is in the plus z direction. This is so since dl into r is equal to delta x I cap into y j cap is equal to y delta x I cap into j cap is equal to y delta x k cap. Following cyclic property of cross products. I cap into j cap is equal to k cap. J cap into k cap is equal to I cap. K cap into I cap is equal to j cap. The field is small in magnitude. 6. Magnetic field on the axis of a circular current loop. In this section, we shall evaluate the magnetic field due to a circular coil along its axis. The evaluation entails summing up the effect of infinitesimal current elements, that is IDL, mentioned in the previous section. We assume that the current I is steady and that the evaluation is carried out in free space, that is vacuum. Figure depicts a circular loop carrying a steady current I. The loop is placed in the YZ plane with its center at the origin O and has a radius R. The x-axis is the axis of the loop. We wish to calculate the magnetic field at the point P on this axis. Let x be the distance of P from the center O of the loop. Consider a conducting element dl of the loop. This is shown in figure. The magnetic field dB of the magnetic field due to dl is given by the Biot-Savart law, equation 11a. dB is equal to mu0 upon 4 pi I mod of dl into r upon r cube, equation number 12. Now r square is equal to x square plus r square. Further, any element of the loop will be perpendicular to the displacement vector from the element to the axial point. For example, the element dl in figure is in the YZ plane, whereas the displacement vector r from dl to the axial point P is in the xy plane. Hence, mod of dl into r is equal to rdl. Thus, dB is equal to mu0 upon 4 pi into idl upon x square plus r square, equation number 13. The direction of dB is shown in figure. It is perpendicular to the plane formed by dl and r. It has an x component dbx and a component perpendicular to x-axis db perpendicular. When the components perpendicular to the x-axis are summed over, they cancel out and we obtain a null result. For example, the dB perpendicular component due to dl is cancelled by the contribution due to the diametrically opposite dl element. Thus, only the x component survives. The net contribution along x direction can be obtained by the integrating dpx is equal to db cos theta over the loop. Cos theta is equal to r upon x square plus r square raised to 1 upon 2. Equation number 14. The angle between r and r is also theta. From equations 13 and 14, dbx is equal to mu0 idl upon 4 pi into r upon x square plus r square raised to 3 upon 2. The summation of elements dl over the loop yields 2 pi r, the circumference of the loop. Thus, the magnetic field at P due to entire circular loop is B is equal to Bx I cap is equal to mu0 ir square upon 2 x square plus r square raised to 3 upon 2 I cap. Equation number 15. As a special case of the above result, we may obtain the field at the center of the loop. Here x is equal to 0 and we obtain B0 is equal to mu0 I upon 2r I cap. Equation number 16. The magnetic field lines due to a circular wire from closed loops and are shown in figure. The direction of the magnetic field is given by another right hand thumb rule stated below. Curl the palm of your right hand around the circular wire with the fingers pointing in the direction of the current. The right hand thumb gives the direction of the magnetic field. Example 6. A straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 cm. Consider the magnetic field B at the center of the arc. A. What is the magnetic field due to the straight segments? B. In what way the contribution to B from the semicircle differs from that of a circular loop, and in what way does it resemble? C. Would your answer be different if the wire were bent into a semicircular arc of the same radius but in the opposite way? Solution. A. dl and r for each element of the straight segments are parallel. Therefore, dl into r is equal to 0. Straight segments do not contribute to mode of B. B. For all segments of the semicircular arc, dl into r are all parallel to each other, that is, into the plane of the paper. All such contributions add up in magnitude. Hence, direction of B for a semicircular arc is given by the right hand rule and magnitude is half that of a circular loop. Thus, B is 1.9 into 10 raised to minus 4 Tesla, normal to the plane of the paper going into it. C. Same magnitude of B but opposite in direction to that in B. Example 7. Consider a tightly wound 100-ton coil of radius 10 cm carrying a current of 1 ampere. What is the magnitude of the magnetic field at the center of the coil? Solution. Since the coil is tightly wound, we may take each circular element to have the same radius r is equal to 10 cm is equal to 0.1 meter. The number of turns n is equal to 100. The magnitude of the magnetic field is B is equal to mu 0 Ni upon 2r is equal to 4 pi into 10 raised to minus 7 into 10 raised to 2 into 1 divided by 2 into 10 raised to minus 1 is equal to 2 pi into 10 raised to minus 4 is equal to 6.28 into 10 raised to minus 4 Tesla. 7. Ampere's circuital law. There is an alternative and appealing way in which the Biot-Savart law may be expressed. Ampere's circuital law considers an open surface with a boundary. The surface has current passing through it. We consider the boundary to be made up of a number of small line elements. Consider one such element of length dl. We take the value of the tangential component of the magnetic field bt at this element and multiply it by the length of that element dl. Note, bt dl is equal to b into dl. All such products are added together. We consider the limit as the lengths of elements get smaller and their number gets larger. The sum then tends to an integral. Ampere's law states that this integral is equal to mu 0 times the total current passing through the surface, that is, closed integral b into dl is equal to mu 0 I. Equation number 17a, where I is the total current through the surface. The integral is taken over the closed loop coinciding with the boundary C of the surface. The relation above involves a sign convention given by the right hand rule. Let the fingers of the right hand be curled in the sense of the boundary is traversed in the loop integral close integral b into dl. Then the direction of the thumb gives the sense in which the current I is regarded as positive. For several applications, a much simplified version of equation 17a proves sufficient. We shall assume that in such cases, it is possible to choose the loop that is called an Amperian loop such that at each point of the loop either 1. B is tangential to the loop and is a non-zero constant B, or 2. B is normal to the loop, or 3. B vanishes. Now let L be the length part of the loop for which B is tangential. Let IE be the current enclosed by the loop. Then equation 17 reduces to BL is equal to mu 0 IE. Equation number 17b. When there is a system with a symmetry, such as for a straight infinite current carrying wire in figure, the Ampere's law enables an easy evaluation of the magnetic field. The boundary of the loop chosen is a circle, and magnetic field is tangential to the circumference of the circle. The law gives for the left hand side of equation 17b, B into 2 pi r. We find that the magnetic field at a distance r outside the wire is tangential and given by B into 2 pi r is equal to mu 0 I. B is equal to mu 0 I upon 2 pi r. Equation number 18. The above result for the infinite wire is interesting from several points of view. 1. It implies that the field at every point on a circle of radius r with the wire along the axis is the same in magnitude. In other words, the magnetic field possesses what is called a cylindrical symmetry. The field that normally can depend on 3 coordinates depends only on 1 r. Whenever there is symmetry, the solutions simplify. 2. The field direction at any point on this circle is tangential to it. Thus, the lines of constant magnitude of magnetic field form concentric circles. Notice now in figure, the iron fillings form concentric circles. These lines called magnetic field lines form closed loops. This is unlike the electrostatic field lines which originate from positive charges and end at negative charges. The expression for the magnetic field of a straight wire provides a theoretical justification to Oersted's experiments. 3. Another interesting point to note is that even though the wire is infinite, the field due to it at a non-zero distance is not infinite. It tends to blow up only when we come very close to the wire. The field is directly proportional to the current and inversely proportional to the distance from the infinitely long current source. 4. There exists a simple rule to determine the direction of the magnetic field due to a long wire. This rule, called the right hand rule, is grasp the wire in your right hand with your extended thumb pointing in the direction of the current. Your fingers will curl around in the direction of the magnetic field. Ampere's circuital law is not new in content from Biot-Savart law. Both relate the magnetic field and the current, and both express the same physical consequences of a steady electrical current. Ampere's law is to Biot-Savart law what Gauss's law is to Coulomb's law. Both Ampere's and Gauss's law relate a physical quantity on the periphery or boundary, that is, magnetic or electric field, to another physical quantity, namely the source in the interior, that is, current or charge. We also note that Ampere's circuital law holds for steady currents which do not fluctuate with time. The following example will help us understand what is meant by the term enclosed current. Example 8. Figure shows a long straight wire of a circular cross-section, that is radius A, carrying steady current I. The current I is uniformly distributed across this cross-section. Calculate the magnetic field in the region R is less than A and R is greater than A. Solution. A. Consider the case R is greater than A. The Amperian loop, labeled 2, is the circle concentric with the cross-section. For this loop, L is equal to 2 pi r. IE is equal to current enclosed by the loop is equal to I. The result is the familiar expression for a long straight wire. B 2 pi r is equal to mu 0 I. B is equal to mu 0 I upon 2 pi r. Equation number 19a. B is directly proportional to 1 upon r, where r is greater than a. B. Consider the case r is less than a. The Amperian loop is a circle labeled 1. For this loop, taking the radius of the circle to be r, L is equal to 2 pi r. Now, the current enclosed IE is not I, but is less than this value. Since the current distribution is uniform, the current enclosed is IE is equal to I pi r square upon pi a square is equal to I r square upon a square. Using Ampere's law, B 2 pi r is equal to mu 0 I r square upon a square. B is equal to r into mu 0 I upon 2 pi a square. Equation number 19b. B is directly proportional to r, where r is less than a. Figure shows a plot of the magnitude of B with distance r from the center of the wire. The direction of the field is tangential to the respective circular loop 1 or 2 and given by the right hand rule described earlier in this section. This example possesses the required symmetry so that Ampere's law can be applied readily. It should be noted that while Ampere's circular law holds for any loop, it may not always facilitate an evolution of the magnetic field in every case. For example, for the case of the circular loop, it cannot be applied to extract the simple expression B is equal to mu 0 I upon 2r, equation 16, for the field at the center of the loop. However, there exists a large number of situations of high symmetry where the law can be conveniently applied. We shall use it in the next section to calculate the magnetic field produced by two commonly used and very useful magnetic systems, the solenoid and the toroid. 8. The solenoid and the toroid. The solenoid and the toroid are two pieces of equipment which generate magnetic fields. The television uses the solenoid to generate magnetic fields needed. The Cyclotron uses a combination of both to generate the high magnetic fields required. In both solenoid and toroid, we come across a situation of high symmetry where Ampere's law can be conveniently applied. The solenoid. We shall discuss a long solenoid. By long solenoid, we mean that the solenoid's length is large compared to its radius. It consists of a long wire wound in the form of a helix, where the neighboring turns are closely spaced, so each turn can be regarded as a circular loop. The net magnetic field is the vector sum of the fields due to all the turns. Enameled wires are used for winding so that turns are insulated from each other. Figure displays the magnetic field lines for a finite solenoid. We show a section of this solenoid in an enlarged manner in Figure A. Figure B shows the entire finite solenoid with its magnetic field. In Figure A, it is clear from the circular loops that the field between two neighboring turns vanishes. In Figure B, we see that the field at the interior midpoint P is uniform, strong, and along the axis of the solenoid. The field at the exterior midpoint Q is weak and moreover is along the axis of the solenoid with no perpendicular or normal component. As the solenoid is made longer, it appears like a long cylindrical metal sheet. Figure represents this idealized picture. The field outside the solenoid approaches zero. We shall assume that the field outside is zero. The field inside becomes everywhere parallel to the axis. Consider a rectangular Amperian loop ABCD. Along CD, the field is zero, as argued above. Along transverse sections BC and AD, the field component is zero. Thus, these two sections make no contribution. Let the field along AB, B, B. Thus, the relevant length of the amperian loop is L is equal to H. Let N be the number of turns per unit length. Then the total number of turns is NH. The enclosed current is IE is equal to I NH, where I is the current in the solenoid. From Ampere's circuital law, equation 17b. BL is equal to mu 0 IE. BH is equal to mu 0 I NH. B is equal to mu 0 NI. Equation number 20. The direction of the field is given by the right hand rule. The solenoid is commonly used to obtain a uniform magnetic field. We shall see in the next chapter that a large field is possible by inserting a soft iron core inside the solenoid. The toroid. The toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. It can be viewed as a solenoid, which has been bent into a circular shape to close on itself. It is shown in figure carrying a current I. The magnetic field in the open space inside, that is point P, and exterior to the toroid, that is point Q, is 0. The field B inside the toroid is constant in magnitude for the ideal toroid of closely wound turns. Figure shows a sectional view of the toroid. The direction of the magnetic field inside is clockwise as per the right-hand thumb rule for circular loops. 3 circular amperian loops 1, 2 and 3 are shown by dashed lines. By symmetry, the magnetic field should be tangential to each of them and constant in magnitude for a given loop. The circular areas bounded by loops 2 and 3 both cut the toroid, so that each turn of current carrying wire is cut once by the loop 2 and twice by the loop 3. Let the magnetic field along loop 1 be B1 in magnitude. Then in Ampere's circuital law, equation 17a, L is equal to 2 pi R1. However, the loop encloses no current, so IE is equal to 0. Thus, B1 2 pi R1 is equal to mu 0, 0. B1 is equal to 0. Thus, the magnetic field at any point P in the open space inside the toroid is 0. We shall now show that magnetic field at Q is likewise 0. Let the magnetic field along loop 3 be B3. Once again from Ampere's law, L is equal to 2 pi R3. However, from the sectional cut, we see that the current coming out of the plain paper of the paper is cancelled exactly by the current going into it. Thus, IE is equal to 0 and B3 is equal to 0. Let the magnetic field inside the solenoid be B. We shall now consider the magnetic field at S. Once again, we employ Ampere's law in the form of equation 17a. We find L is equal to 2 pi R. The current enclosed IE is for n turns of toroidal coil Ni. B 2 pi R is equal to mu 0 Ni. B is equal to mu 0 Ni upon 2 pi R, equation 21. We shall now compare the two results. For a toroid and solenoid, we re-express equation 21 to make the comparison easier with the solenoid result given in equation 20. Let R be the average radius of the toroid and N be the number of turns per unit length. Then N is equal to 2 pi R N is equal to average perimeter of the toroid into number of turns per unit length, and thus B is equal to mu 0 Ni, equation 22. That is the result for the solenoid. In an ideal toroid, the coils are circular. In reality, the turns of the toroidal coil form a helix, and there is always a small magnetic field external to the toroid. Magnetic confinement. We have seen in previous section. See also the box on helical motion of charged particles earlier in this chapter, that orbits of charged particles are helical. If the magnetic field is non-uniform but does not change much during one circular orbit, then the radius of the helix will decrease as it enters stronger magnetic field, and the radius will increase when it enters weaker magnetic fields. We consider two solenoids at a distance from each other enclosed in an evacuated container. See figure below where we have not shown the container. Charged particles moving in the region between the two solenoids will start with a small radius. The radius will increase as field decreases, and the radius will decrease again as field due to the second solenoid takes over. The solenoids act as a mirror or reflector. See the direction of F as the particle approaches coil 2 in the figure. It has the horizontal component against the forward motion. This makes the particles turn back when they approach the solenoid. Such an arrangement will act like magnetic bottle or magnetic container. The particles will never touch the sides of the container. Such magnetic bottles are of great use in confining the high energy plasma in fusion experiments. The plasma will destroy any other form of material container because of its high temperature. Another useful container is a toroid. Toroids are expected to play a key role in the tokamak, an equipment for plasma confinement in fusion power reactors. There is an international collaboration called the International Thermonuclear Experimental Reactor, that is ITER, being set up in France for achieving controlled fusion, of which India is the collaborating nation. Example 9. A solenoid of length 0.5 meter has a radius of 1 centimeter and is made up of 500 tons. It carries a current of 5 ampere. What is the magnitude of the magnetic field inside the solenoid? Solution. The number of turns per unit length is N is equal to 500 divided by 0.5 is equal to 1000 turns per meter. The length L is equal to 0.5 meter and radius R is equal to 0.01 meter. Thus, L upon A is equal to 50. That is, 1 is much greater than A. Hence, we can use the long solenoid formula, namely equation 20. B is equal to mu 0 Ni is equal to 4 pi into 10 raised to minus 7 into 10 raised to 3 into 5 is equal to 6.28 into 10 raised to minus 3 Tesla. 10. Force between two parallel currents, the ampere. There exists a magnetic field due to a conductor carrying a current which obeys the Biot-Savart law. An external magnetic field will exert a force on a current carrying conductor. This follows from the Lorentz force formula. Thus, it is logical to expect that two current carrying conductors placed near each other will exert magnetic forces on each other. In the period 1820 to 25, Ampere studied the nature of this magnetic force and its dependence on the magnitude of the current, on the shape and size of the conductors as well as the distances between the conductors. In this section, we shall take the simple example of two parallel current carrying conductors, which will perhaps help us to appreciate Ampere's painstaking work. Figure shows two long parallel conductors A and B separated by a distance d and carrying parallel currents Ia and Ib respectively. The conductor A produces the same magnetic field Ba at all points along the conductor B. The right-hand rule tells us that the direction of this field is downwards when the conductors are placed horizontally. Its magnitude is given by equation 19a or from Ampere's circuital law. Ba is equal to mu 0 Ia upon 2 pi d. The conductor B carrying a current Ib will experience a sideways force due to the field Ba. The direction of this force is towards the conductor A. We label this force as FBA. The force on a segment L of B due to A. The magnitude of this force is given by equation 4. FBA is equal to IB L BA is equal to mu 0 IA IB upon 2 pi d into L. It is of course possible to compute the force on A due to B. From consideration similar to above, we can find the force FAB on a segment of length L of A due to the current in B. It is equal in magnitude to FBA and directed towards B. Thus, FBA is equal to minus FAB. Equation number 24. Note that this is consistent with Newton's third law. Thus, at least for parallel conductors and steady currents, we have shown that the Biot-Savart law and the Lorentz force yield results in accordance with Newton's third law. We have seen from above that currents flowing in the same direction attract each other. One can show that oppositely directed currents repel each other. Thus, parallel currents attract and antiparallel currents repel. This rule is the opposite of what we find in electrostatics. Like same sign charges repel each other, but like parallel currents attract each other. Let FBA represent the magnitude of the force FBA per unit length. Then, from equation 23, FBA is equal to mu 0 IA IB upon 2 pi d. Equation number 25. The above expression is used to define the ampere, that is A, which is one of the 7 SI base units. The ampere is the value of that steady current which, when maintained in each of the two very long, straight, parallel conductors of negligible cross-section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 raised to minus 7 newtons per meter of length. This definition of the ampere was adopted in 1946. It is a theoretical definition. In practice, one must eliminate the effect of the Earth's magnetic field and substitute very long wires by multi-turn coils of appropriate geometries. An instrument called the current balance is used to measure this mechanical force. The SI unit of charge, namely the coulomb, can now be defined in terms of the ampere. When a steady current of 1A is set up in a conductor, the quantity of charge that flows through its cross-section in 1 second is 1 coulomb, that is 1C. Roget spiral for attraction between parallel currents. Magnetic effects are generally smaller than electric effects. As a consequence, the force between currents is rather small because of the smallness of the factor mu. Hence, it is difficult to demonstrate attraction or repulsion between currents. Thus, for 5 ampere currents in each wire at a separation of 1 cm, the force per meter would be 5 into 10 raised to minus 4 Newton, which is about 50 microgram weight. It would be like pulling a wire by a string going over a pulley to which 50 microgram weight is attached. The displacement of the wire would be quite unnoticeable. With the use of a soft spring, we can increase the effective length of the parallel current, and by using mercury, we can make the displacement of even a few millimeters observable very dramatically. You will also need a constant current supply, giving a constant current of about 5 ampere. Take a soft spring whose natural period of oscillations is about 0.5 to 1 second. Hang it vertically and attach a pointed tip to its lower end, as shown in the figure here. Take some mercury in a dish and adjust the spring such that the tip is just above the mercury surface. Take the DC current source, connect one of its terminals to the upper end of the spring and dip the other terminal in mercury. If the tip of the spring touches mercury, the circuit is completed through mercury. Let the DC source be put off to begin with. Let the tip be adjusted so that it just touches the mercury surface. Switch on the constant current supply and watch the fascinating outcome. The spring shrinks with a jerk. The tip comes out of mercury, that is just by a mm or so. The circuit is broken, the current stops, the spring relaxes and tries to come back to its original position. The tip again touches mercury, establishing a current in the circuit, and cycle continues with tick tick tick. In the beginning, you may require some small adjustments to get a good effect. Keep your face away from mercury vapors as they are poisonous. Do not inhale mercury vapors for long. Example 10. The horizontal component of the Earth's magnetic field at a certain place is 3.0 into 10 raised to minus 5 Tesla, and the direction of the field is from the geographic south to the geographic north. A very long straight conductor is carrying a steady current of 1 ampere. What is the force per unit length on it when it is placed on a horizontal table and the direction of the current is A. East to west, B. South to north? Solution. F is equal to IL into B. F is equal to ILB sin theta. The force per unit length is F is equal to F upon L is equal to IB sin theta. A. When the current is flowing from east to west, theta is equal to 90 degree. Hence, F is equal to IB sin 90 degree, where sin 90 degree is equal to 1 into 3 into 10 raised to minus 5 is equal to 3 into 10 raised to minus 5 Newton per meter. This is larger than the value 2 into 10 raised to minus 7 Newton per meter quoted in the definition of the ampere. Hence, it is important to eliminate the effect of the Earth's magnetic field and other stray fields while standardize the ampere. The direction of the force is downwards. This direction may be obtained by the directional property of cross product of vectors. B. When the current is flowing from south to north, theta is equal to 0 degree. F is equal to 0. Hence, there is no force on the conductor. Torque on current loop magnetic dipole. Torque on a rectangular current loop in a uniform magnetic field. We now show that a rectangular loop carrying a steady current I and placed in a uniform magnetic field experiences a torque. It does not experience a net force. This behavior is analogous to that of electric dipole in a uniform electric field. We first consider the simple case when the rectangular loop is placed such that the uniform magnetic field B is in the plane of the loop. This is illustrated in figure. The field exerts no force on the two arms AD and BC of the loop. It is perpendicular to the arm AB of the loop and exerts a force F1 on it, which is directed into the plane of the loop. Its magnitude is F1 is equal to IBB. Similarly, it exerts a force F2 on the arm CD and F2 is directed out of the plane of the paper. F2 is equal to IBB is equal to F1. Thus, the net force on the loop is 0. There is a torque on the loop due to the pair of forces F1 and F2. Figure shows a view of the loop from the AD end. It shows that the torque on the loop tends to rotate it anti-clockwise. This torque is in magnitude. Tau is equal to F1 A upon 2 plus F2 A upon 2 is equal to IBB A upon 2 plus IBB A upon 2 is equal to IABB is equal to IAB. Equation number 26, where A is equal to AB is the area of the rectangle. We next consider the case when the plane of the loop is not along the magnetic field but makes an angle with it. We take the angle between the field and the normal to the coil to be angle theta. That is, the previous case corresponds to theta is equal to pi by 2. Figure illustrates this general case. The forces on the arms BC and DA are equal, opposite, and act along the axis of the coil, which connects the centers of mass of BC and DA. Being collinear along the axis, they cancel each other. Resulting is no net force or torque. The forces on arms AB and CD are F1 and F2. They too are equal and opposite, with magnitude F1 is equal to F2 is equal to IBB. But they are not collinear. This results in a couple as before. The torque is, however, less than the earlier case, when plane of loop was along the magnetic field. This is because the perpendicular distance between the forces of the couple has decreased. Figure is a view of the arrangement from the AD end, and it illustrates these two forces constituting a couple. The magnitude of the torque on the loop is tau is equal to F1 A upon 2 sin theta plus F2 A upon 2 sin theta is equal to I AB B sin theta is equal to IAB sin theta. Equation number 27. As theta tends to 0, the perpendicular distance between the forces of the couple also approaches 0. This makes the forces collinear and the net force and torque 0. The magnetic moment of the current loop as the torques in equations 26 and 27 can be expressed as vector product of the magnetic moment of the coil and the magnetic field. We define the magnetic moment of the current loop as M is equal to IA. Equation number 28. Where the direction of the area vector A is given by the right hand thumb rule and is directed into the plane of the paper in figure, then as the angle between M and B is theta, equations 26 and 27 can be expressed by one expression. Tau is equal to M into B. Equation number 29. This is analogous to the electrostatic case, that is, electric dipole of dipole moment PE in an electric field E. Tau is equal to PE into E. As is clear from equation 28, the dimensions of the magnetic moment are AL square and its unit is ampere into meter square. From equation 29, we see that the torque T vanishes when M is either parallel or antiparallel to the magnetic field B. This indicates a state of equilibrium as there is no torque on the coil. This also applies to any object with a magnetic moment M. When M and B are parallel, the equilibrium is a stable one. Any small rotation of the coil produces a torque, which brings it back to its original position. When they are antiparallel, the equilibrium is unstable, as any rotation produces a torque, which increases with the amount of rotation. The presence of this torque is also the reason why a small magnet or any magnetic dipole aligns itself with the external magnetic field. If the loop has n closely wound turns, the expression for torque, equation 29, still holds with M is equal to NIA. Equation number 30. Example 11. A 100-ton closely wound circular coil of radius 10 cm carries a current of 3.2 ampere. A. What is the field at the center of the coil? B. What is the magnetic moment of this coil? The coil is placed in a vertical plane and is free to rotate about a horizontal axis, which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists, such that initially the axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degrees under the influence of the magnetic field. C. What are the magnitudes of the torques on the coil in the initial and final position? D. What is the angular speed acquired by the coil when it has rotated by 90 degrees? the moment of inertia of the coil is 0.1 kg into meter square. Solution. A. From equation 16, B is equal to mu0 Ni upon 2R. Here N is equal to 100, I is equal to 3.2 A and R is equal to 0.1 M. Hence, B is equal to 4 pi into 10 raised to minus 7 into 10 raised to 2 into 3.2 divided by 2 into 10 raised to minus 1 is equal to 4 into 10 raised to minus 5 into 10 divided by 2 into 10 raised to minus 1 using pi into 3.2 is equal to 10 is equal to 2 into 10 raised to minus 3 t. The direction is given by the right hand thumb rule. B. The magnetic moment is given by equation 30. M is equal to NIA is equal to Ni pi r square is equal to 100 into 3.2 into 3.14 into 10 raised to minus 2 is equal to 10 am square. The direction is once again given by the right hand thumb rule. C. Tau is equal to mod of m into b from equation 29 is equal to mb sin theta. Initially, theta is equal to 0. Thus, initial torque tau I is equal to 0. Finally, theta is equal to pi by 2 or 90 degree. Thus, final torque tau F is equal to mb is equal to 10 into 2 is equal to 20 Newton into meter. D. From Newton's second law, I d omega upon dt is equal to mb sin theta, where I is the moment of inertia of the coil. From chain rule, d omega upon dt is equal to d omega upon d theta into d theta upon dt is equal to d omega upon d theta into omega. Using this, I omega d omega is equal to mb sin theta d theta. Integrating from theta is equal to 0 to theta is equal to pi by 2. I integration from 0 to omega f omega d omega is equal to mb integration from 0 to pi by 2 sin theta d theta. I omega square f upon 2 is equal to minus mb cos theta 0 to pi by 2 is equal to mb. Omega f is equal to 2 mb upon I raised to 1 upon 2 is equal to 2 into 20 divided by 10 raised to minus 1 raised to 1 upon 2 is equal to 20 second inverse. Example 12. A current carrying circular loop lies on a smooth horizontal plane. Can a uniform magnetic field be set up in such a manner that the loop turns around itself, that is, turns about the vertical axis? B. A current carrying circular loop is located in a uniform external magnetic field. If the loop is free to turn, what is its orientation of the stable equilibrium? Show that in this orientation, the flux of the total field, that means external field plus field produced by the loop, is maximum. C. A loop of irregular shape carrying current is located in an external magnetic field. If the wire is flexible, why does it change to a circular shape? Solution. A. No, because that would require tau to be in the vertical direction. But tau is equal to Ia into B, and since A of the horizontal loop is in the vertical direction, tau would be in the plane of the loop for any B. B. Orientation of stable equilibrium is 1, where the area vector A of the loop is in the direction of external magnetic field. In this orientation, the magnetic field produced by the loop is in the same direction as external field, both normal to the plane of the loop, thus giving rise to maximum flux of the total field. C. It assumes circular shape with its plane normal to the field to maximize flux, since for a given perimeter, a circle encloses greater area than any other shape. Circular current loop as a magnetic dipole. In this section, We shall consider the elementary magnetic element, the current loop. We shall show that the magnetic field at large distances due to current in a circular current loop is very similar in behavior to the electric field of an electric dipole. In section, we have evaluated the magnetic field on the axis of a circular loop of a radius r carrying a steady current I. The magnitude of this field is equation 15. B is equal to mu 0 I r square upon 2 x square plus r square raised to 3 upon 2, and its direction is along the axis and given by the right hand thumb rule. Here x is the distance along the axis from the center of the loop. For x is more greater than r, we may drop the r square term in the denominator. Thus, B is equal to mu 0 I r square upon 2x cube. The area of the loop A is equal to pi r square. Thus, B is equal to mu 0 IA upon 2 pi x cube. As earlier, we defined the magnitude moment M to have a magnitude IA. M is equal to IA. Hence, B is approximately equal to mu 0 M upon 2 pi x cube is equal to mu 0 upon 4 pi into 2m upon x cube. Equation number 31a. The expression of equation 31a is very similar to an expression obtained earlier for the electric field of a dipole. The similarity may be seen if we substitute mu 0 to 1 upon epsilon 0, m to Pe, that is electrostatic dipole, B to E, that is electrostatic field. We then obtain E is equal to 2 Pe upon 4 pi epsilon 0 x cube, which is precisely the field for an electric dipole at a point on its axis. It can be shown that the above analogy can be carried further. The electric field on the perpendicular bisector of the dipole is given by E is approximately equal to Pe upon 4 pi epsilon 0 x cube, where x is the distance from the dipole. If we replace P to M and mu 0 to 1 upon epsilon 0 in the above expression, we obtained the result for B for a point in the plane of the loop at a distance x from the center, for x is more greater than r. B is approximately equal to mu 0 upon 4 pi into m upon x cube, where x is more greater than r. Equation number 31b. The results given by equations 31a and 31b become exact for a point magnetic dipole. The results obtained above can be shown to apply to any planar loop. A planar current loop is equivalent to a magnetic dipole of dipole moment M is equal to Ia, which is the analog of electric dipole moment P. Not, however, a fundamental difference. An electric dipole is built up of two elementary units, the charges or electric monopoles. In magnetism, a magnetic dipole or a current loop is the most elementary element. The equivalent of electric charges, that is magnetic monopoles, are not known to exist. We have shown that a current loop 1. Produces a magnetic field and behaves like a magnetic dipole at large distances, and 2. Is subject to torque like a magnetic needle. This led Ampere to suggest that all magnetism is due to circulating currents. This seems to be partly true, and no magnetic monopoles have been seen so far. However, elementary particles such as an electron or a proton also carry an intrinsic magnetic moment, not accounted by circulating currents. The magnetic dipole moment of a revolving electron. We shall read about the Bohr model of the hydrogen atom. You may perhaps have heard of this model, which was proposed by the Danish physicist Niels Bohr in 1911 and was a stepping stone to a new kind of mechanics, namely quantum mechanics. In the Bohr model, the electron, that is a negatively charged particle, revolves around a positively charged nucleus much as a planet revolves around the sun. The force in the former case is the electrostatic, that is Coulomb force, while it is gravitational for the planet-sun case. We saw this Bohr picture of the electron in figure. The electron of charge minus E is equal to plus 1.6 into 10 raised to minus 19 Coulomb, performs uniform circular motion around a stationary heavy nucleus of charge plus Ze. This constitutes a current I, where I is equal to E upon T, equation number 32, and T is the time period of revolution. Let R be the orbital radius of the electron and V the orbital speed. Then T is equal to 2 pi R upon V, equation number 33. Substituting in equation 32, we have I is equal to EV upon 2 pi R. There will be a magnetic moment, usually denoted by mu L, associated with this circulating current. From equation 28, its magnitude is mu L is equal to I pi R square is equal to EVR upon 2. The direction of this magnetic moment is into the plane of the paper in figure. This follows from the right-hand rule discussed earlier and the fact that the negatively charged electron is moving anti-clockwise, leading to a clockwise current. Multiplying and dividing the right-hand side of the above expression by the electron mass me, we have mu L is equal to E upon 2 me into me Vr is equal to E upon 2 me into L. Equation number 34a. Here, L is the magnitude of the angular momentum of the electron about the central nucleus, that is orbital angular momentum. Vectorially, mu L is equal to minus E upon 2 me into L. Equation number 34b. The negative sign indicates that the angular momentum of the electron is opposite in direction to the magnetic moment. Instead of electron with charge minus E, if we had taken a particle with charge plus Q, the angular momentum and magnetic moment would be in the same direction. The ratio mu L upon L is equal to E upon 2 me, equation number 35, is called the gyromagnetic ratio and is a constant. Its value is 8.8 into 10 raised to 10 Coulomb per kilogram for an electron, which has been verified by experiments. The fact that even at an atomic level there is a magnetic moment confirms Ampere's bold hypothesis of atomic magnetic moments. This, according to Ampere, would help one to explain the magnetic properties of materials. Can one assign a value to this atomic dipole moment? The answer is yes. One can do so within the Bohr model. Bohr hypothesized that the angular momentum assumes a discrete set of values, namely L is equal to NH upon 2 pi, equation number 36, where N is a natural number, N is equal to 1, 2, 3, and H is a constant named after Max Planck, that is Planck's constant, with a value H is equal to 6.626 into 10 raised to minus 34 joule into second. Our aim here is merely to use it to calculate the elementary dipole moment. This condition of discreteness is called the Bohr quantization condition. Take the value n is equal to 1. We have from equation 34 that mu L minimum is equal to E upon 4 pi me into H is equal to 1.60 into 10 raised to minus 19 into 6.63 into 10 raised to minus 34 divided by 4 into 3.14 into 9.11 into 10 raised to minus 31 is equal to 9.27 into 10 raised to minus 24 ampere meter square. Equation number 37, where the subscript min stands for minimum. This value is called the Bohr magneton. Any charge in uniform circular motion would have an associated magnetic moment given by an expression similar to equation 34. This dipole moment is labeled as the orbital magnetic moment, hence the subscript L in mu L. Besides the orbital moment, the electron has an intrinsic magnetic moment, which has the same numerical value as given in equation 37. It is called the spin magnetic moment. But we hasten to add that it is not as though the electron is spinning. The electron is an elementary particle and it does not have an axis to spin around like a top or our Earth. Nevertheless, it does possess this intrinsic magnetic moment. The microscopic roots of magnetism in iron and other materials can be traced back to this intrinsic spin magnetic moment. The moving coil galvanometer. Currents and voltages in circuits have been discussed in previous chapter. But how do we measure them? How do we claim that current in a circuit is 1.5 ampere or the voltage drop across a resistor is 1.2 volt? Figure exhibits a very useful instrument for this purpose. The moving coil galvanometer, that is MCG. It is a device whose principle can be understood on the basis of our discussion in previous section. The galvanometer consists of a coil with many turns free to rotate about a fixed axis. Figure. In a uniform radial magnetic field, there is a cylindrical soft iron core which not only makes the field radial but also increases the strength of the magnetic field. When a current flows through the coil, a torque acts on it. This torque is given by equation 26 to be tau is equal to NIAB, where the symbols have their usual meaning. Since the field is radial by design, we have taken sin theta is equal to 1 in the above expression for the torque. The magnetic torque NIAB tends to rotate the coil. A spring SP provides a counter torque K phi that balances the magnetic torque NIAB, resulting in a steady angular deflection phi. In equilibrium, K phi is equal to NIAB, where K is the torrential constant of the spring, that is the restoring torque per unit twist. The deflection phi is indicated on the scale by a pointer attached to the spring. We have phi is equal to NAB upon K into I, equation number 38. The quantity in brackets is the constant for a given galvanometer. The galvanometer can be used in a number of ways. It can be used as a detector to check if a current is flowing in the circuit. We have come across this usage in the Wheaton's bridge arrangement. In this usage, the neutral position of the pointer when no current is flowing through the galvanometer is in the middle of the scale and not at the left end. Depending on the direction of the current, the pointer deflection is either to the right or the left. The galvanometer cannot as such be used as an ammeter to measure the value of the current in a given circuit. This is for two reasons. 1. Galvanometer is a very sensitive device. It gives a full-scale deflection for a current of the order of mu A. 2. For measuring currents, the galvanometer has to be connected in series, and as it has a large resistance, this will change the value of the current in the circuit. To overcome these difficulties, one attaches a small resistance Rs, called shunt resistance, in parallel with the galvanometer coil, so that most of the current passes through the shunt. The resistance of this arrangement is Rg Rs upon Rg plus Rs is approximately equal to Rs if Rg is more greater than Rs. If Rs has small value in relation to the resistance of the rest of the circuit Rg, the effect of introducing the measuring instrument is also small and negligible. This arrangement is schematically shown in figure. The scale of this ammeter is calibrated and then graduated to read of the current value with ease. We define the current sensitivity of the galvanometer as the deflection per unit current. From equation 38, this current sensitivity is phi upon I is equal to NAB upon K. Equation number 39. A convenient way for the manufacturer to increase the sensitivity is to increase the number of turns N. We choose galvanometers having sensitivities of value required by our experiment. The galvanometer can also be used as a voltmeter to measure the voltage across a given section of the circuit. For this, it must be connected in parallel with that section of the circuit. Further, it must draw a very small current, otherwise the voltage measurement will disturb the original setup by an amount which is very large. Usually, we like to keep the disturbance due to the measuring device below 1%. To ensure this, a large resistance R is connected in series with the galvanometer. This arrangement is schematically depicted in figure. Note that the resistance of the voltmeter is now Rg plus Rr is approximately equal to R, large. The scale of the voltmeter is calibrated to read of the voltage value with ease. We define the voltage sensitivity as the deflection per unit voltage. From equation 38, phi upon I is equal to NAB upon K into I upon V is equal to NAB upon K into 1 upon R. Equation number 40. An interesting point to note is that increasing the current sensitivity may not necessarily increase the voltage sensitivity. Let us take equation 39, which provides a measure of current sensitivity. If N to 2N, that is, we double the number of turns, then phi upon I to phi upon I. Thus, the current sensitivity doubles. However, the resistance of the galvanometer is also likely to double, since it is proportional to the length of the wire. In equation 40, N to 2N and R to 2R, thus the voltage sensitivity phi upon V to phi upon V remains unchanged. So in general, the modification needed for conversion of a galvanometer to an ammeter will be different from what is needed for converting it into a voltmeter. Example 13. In the circuit, the current is to be measured. What is the value of the current if the ammeter shown A is a galvanometer with a resistance Rg is equal to 60.00 ohm. B is a galvanometer described in A but converted to an ammeter by a shunt resistance Rs is equal to 0.02 ohm. C is an ideal ammeter with zero resistance. Solution. A. Total resistance in the circuit is Rg plus 3 is equal to 63 ohm. Hence, I is equal to 3 divided by 63 is equal to 0.048 ampere. B. Resistance of the galvanometer converted to an ammeter is Rg/Rs upon Rg plus Rs is equal to 60 ohm into 0.02 ohm divided by 60 plus 0.02 ohm is approximately equal to 0.02 ohm. Total resistance in the circuit is 0.02 ohm plus 3 ohm is equal to 3.02 ohm. Hence, I is equal to 3 divided by 3.02 is equal to 0.99 ampere. C. For the ideal ammeter with zero resistance, I is equal to 3 divided by 3 is equal to 1.00 ampere.